Okay guys, another video here dealing with electrochemistry. This one relates electrochemistry to thermodynamics. So the topics that we learned about in the last chapter can be related to the topics that we're learning about in electrochemistry through what's called the Nernst equation. And it allows us to relate cell potentials to free energy changes. Likewise, we can also perform calculations involving equilibrium constants and reaction quotients as well. So the equations that you need in order to do these types of calculations are all listed on this slide here. The most important thing to remember is that the Gibbs energy of a reaction and the equilibrium constant, they are both related to the cell potential for a redox reaction. And here I'm articulating how that occurs. In physics, when you do electrical work, you can calculate the amount of work done by taking the charge and multiplying by the potential difference through which that charge moves. Okay? So electrical work can be related to a potential difference. Now, in the last chapter on thermodynamics, we learned that one interpretation of the Gibbs free energy is that it represents the maximum work done by a chemical reaction. And so what we're doing in this equation is we're using this idea from physics and then this relationship from thermochemistry to calculate the Gibbs energy of a reaction from the amount of charge transferred and the potential difference for that electrochemical reaction. So we've got this formula here relating the free energy to the cell potential. The proportionality factor here is the amount of charge that is transferred. So we have minus the number of moles of electrons that are transferred times the Faraday constant, which is a constant 96,485 coulombs per moles of electrons. The energy that you get out of this, or I should say the unit that you get out of this will be energy per mole, so kilojoules per mole of reaction. By using the relationship between the Gibbs free energy and the electron and the equilibrium constant that we learned about in the last chapter, you can then in turn relate the equilibrium constant to the cell potential. And I've skipped the algebra involved, but here is the formula for doing that. So given the equilibrium constant for a reaction, you can calculate the cell potential, or you can rearrange this equation. Given the cell potential, you can calculate the equilibrium constant. R is the gas constant, and you would want to use the joules per mole per Kelvin version of the gas constant. T should be the temperature in Kelvin. N is number of moles transferred, and F is that Faraday constant. A simpler form of this equation that is valid at 25 degrees Celsius, that is, if you plug in the gas constant, you plug in the temperature 298 Kelvin, you plug in the Faraday constant, and then you convert from natural log to log base 10, you get this expression here. And so this is just a faster equation to use. Most of the problems that you're going to be working with are at 25 degrees Celsius, and so you can just get away with using this equation to calculate the cell potential. Or you can rearrange it to calculate K from the cell potential. There are two cell potentials, just like there are two Gibbs free energies, one for standard state conditions and the other for non-standard conditions. Likewise, there are two cell potentials. So the E cell circle is the cell potential for standard state conditions. Before the reaction has occurred, you can calculate the before and after. That gives you sort of the cell potential under standard state conditions. The non-standard cell potential here, you can calculate at any intermediate point in the reaction, and you would need to know the reaction quotient. Okay, so the non-standard cell potential is expressed in terms of the standard cell potential plus this correction factor involving the natural log of the reaction quotient. you can insert the gas constant, insert 25 degrees Celsius, insert the Faraday constant, convert natural log to log, and it gives you this version of the Nernst equation, which is a bit faster to use when your problem is given at 25 degrees Celsius. And so we're going to go through some examples of working with all of these equations. In this first example, we have a particular voltaic cell with a cell potential of 0.650 volts. They want us to calculate the maximum electrical work for this electrochemical cell when 0.5 grams of hydrogen is consumed. So the first thing you need to do is to figure out how many moles of electrons are transferred per mole of reaction. And so you can see that you're going from hydrogen, it's being oxidized to H+, and so that's going to require hydrogen to lose 2 electrons. Likewise, the +2 charge here, you're going to gain 2 electrons to go down to metallic mercury. So there's 2 moles of electrons transferred per mole of reaction. What we need to do is to take the grams of hydrogen that we have that are being consumed, and then to convert that to moles of electrons using stoichiometry. So the conversion factors that we execute are grams of hydrogen to moles of reaction to moles of electrons. And so there are 0.5 grams of hydrogen being consumed. The number of moles of hydrogen that you would have is obtained by dividing by the molar mass. And then there are, 2 moles of electrons for every 1 mole of reaction that occurs. And so this converts us to moles of electrons. We get roughly 0.5 moles of electrons. We can then use this reaction to calculate the maximum amount of work generated when that much hydrogen is consumed. So it's minus the number of moles of electrons times the Faraday constant times the voltage, the cell potential for this electrochemical cell, and it gives us our answer in kilojoules. Okay, and so this indicates that 31 kilojoules of work could be produced at most by this reaction. In this problem, we're being asked to calculate the free energy of the reaction and the equilibrium constant from the cell potential. So we have a redox reaction. We have the table of half reactions. We can deduce by analyzing the electrochemistry here that the number of moles of electrons transferred per mole of reaction is 2, right? You've got 2 silver pluses are being reduced. That's going to require them to gain 2 moles of electrons. We see that the silver ion is being reduced, the iron is being oxidized, so we can calculate the cell potential as cathode minus anode. Since silver is being reduced, that occurs at the cathode, so it's going to be the number for silver minus the number for the iron, which is the anode, and this gives us our cell potential. Okay, now that we know the cell potential, we can use that to calculate the Gibbs energy of reaction according to this equation here. So we just take minus 2 moles of electrons times the Faraday constant times the cell potential that we calculated, and we get a value of minus 240.6 kilojoules per mole. That indicates that the reaction is spontaneous in the forward direction, at least under standard state conditions. In the last step, we're going to use the cell potential to calculate the thermodynamic equilibrium constant using this relationship here. Rearranging this, that is moving the number of moles over here and dividing by the 0.0592, and then taking the anti-logarithm, gives us a value of K that is very large in this case, 1.3 times 10 to the 42, and it indicates that at equilibrium the products are strongly favored. In this example here, we are being asked to calculate, or to determine rather, it's a question, is the reaction spontaneous under these non-standard conditions? And how you do that is you calculate the non-standard cell potential using the Nernst equation, And if the non-standard cell potential is positive, that indicates that the forward direction is spontaneous under these conditions. If it's a negative value, that means that the reverse reaction is spontaneous. So again, you need to work through the electrochemistry. You need to figure out the number of moles of electrons being transferred. Clearly, it's going to be 2 moles of electrons that are being transferred. You need to figure out who's the cathode and who's the anode. We see that the cobalt is oxidized, so the cobalt is the anode. We see that the iron 2 is reduced, so the iron 2 is the cathode. We can calculate the cell potential as cathode minus anode, so we look the numbers up on our table. We get this value for the standard cell potential, and then in order to, so that's one part of the Nernst equation. The other part of the Nernst equation is the reaction quotient term, and so for this reaction, the reaction quotient is products over reactants raised to their stoichiometric powers, and so that's going to be the concentration of the cobalt ion divided by the concentration of the iron 2. Plug in those concentrations to get the reaction quotient, then take both of these numbers, pop them into the Nernst equation, and we get a value of minus 0.13 volts. We see that it's negative, which means that the forward direction under these conditions is not spontaneous. So I'm going to go ahead and stop this video right here.